Can you see my screen, sir?
I mean, not yet the main. Yes, now it has come.
Okay.
But there are some things.
You are going to write, right? Neena?
Yes, I'm going to
There are
write.
certain things
So
on the
it is-
left hand
it is there.
side. Yeah, you can. We can
is there.
see it, and there is something on the left hand side. Can you eliminate that
Yeah.
to make it bigger? Or
Which one? Is it not the big?
now your writing has gone away.
Is it
No,
not the
It
biggest?
is there. It is there. You were
It
writing
is there.
something.
Just
Code
4.
or
Yeah,
something.
that's fine.
Yeah.
It looks fine.
This one.
Maintain this size.
Okay, yeah, that's fine.
Yeah.
Is this okay? Miss handwriting is part is okay?
Yes. Yes. This is quite good.
Yeah. Shall I start? Shall I
So
start?
Dr. Neena Gupta will speak on stably isomorphic 4-dimensional affine domains. So start, Neena.
Yeah. So
Yes.
let me first say express my good wishes to Professor Dilip Patil. Yesterday we heard from many people that he has been a brilliant instructor. So I wish that he will.
Neena, can you speak a little louder?
Yeah, let me just try. Yesterday we heard from many people that Professor Dilip Patil has been a brilliant expositor. So I wish that he would keep continuing this activity even after the supernation, and we will have an opportunity to meet with him regularly. Today, I chose a topic on cancellation problem, but it is slightly different and probably not so well studied. So let me give you a brief introduction. So throughout my talk, small k will denote a field, and for any ring A square bracket n will mean that A is a polynomial ring in n variables over R. So you have n algebraically independent elements x1, x2, xn, and A is a polynomial ring in n variables over R. So we say that two rings A and B, so all my rings are also affine domains. So these are affine domains. So are said to be cancellative if AN is isomorphic to BN. So I should better, are said to be, so I should better say a ring B is said to be cancellative if AN is isomorphic to BN for some integer n greater than equal to 1 and an affine ring A implies A is isomorphic to B. So if this is the condition, then we say the ring B is cancellative. And this problem was known to have an affirmative answer, and this was due to Abhyankar, Eakin, and Heinzer. So this is Abhyankar, Eakin, and Heinzer. And this is a very famous result. The proof is also not difficult and was proved as early as 1972. And they proved that it's true. So if B is a one-dimensional affine domain, one-dimensional affine domain containing Q. And also true if you don't assume containing Q, then you may have to assume that's a normal ring or semi-normal. So let me not get into that. But more than affirmative answers, the counterexamples are more famous. The first counterexample was due to Hochster, and that was based on the existence of non-triviality of tangent bundle on the real sphere. So this was example where you are working over a real sphere and you consider the tangent bundle over that. So that is basically the kernel of the, so let me call this ring R, and you have a ring homomorphism from R3 to R sending. So
Neena,
this,
do you mean x square plus y square minus 1 or plus 1?
oh, sorry, I made a mistake here. So this is z square plus
Z square
minus 1.
minus 1.
So it's a real sphere. So this has three bases, R3. So so I can write it as RE1, RE2, RE3. Then I send E1 to X. So let me denote small x, y, z by the images of capital X, Y, Z in the ring R. E2 to Y and E3 to Z, and P be the kernel of this ring homomorphism, this module homomorphism. Then P is a projective module, and if you look at the symmetric algebra of this projective module P over R and call this ring B, then by the property of this projective module P, so this projective module P from the short exact sequence, you can see it's stably free, but using topology, one can show that B is not free. So using that, one can show that this ring B, after adjoining one more variable, is a polynomial ring in 3 variables over R. And this ring R is such that this isomorphism is an R algebra isomorphism, and B is not R algebra isomorphic to R2, but one can show that this will also imply that B is not isomorphic as over reals. So over reals, this is not isomorphic as affine varieties over real numbers. So we have an example. So here, what is the things we have? It's a 4-dimensional affine domain. In fact, it's a smooth domain.
In your second line, you mean non-isomorphic, right?
Yeah, this is not isomorphic, sorry. So it's a 4-dimensional affine smooth domain over real numbers. So this was a first counter example to the cancellation problem. And so there were some limitations of this example. So because we had an affirmative answer in 1 dimension, then we have an counter example in 4 dimension, and that too over a real number, not over complex. So this was a great achievement in 1989 due to Danielski, and these examples are still very popular. So he constructed examples. So over the field of, so these are 2-dimensional smooth affine, and you can construct it over any field, means of characteristic 0, but you better you take complex number because that was more difficult to ask. And so what was shown is that so it was a family of examples, and so for each integer n greater than equal to 1, let b and b c x y z modulo x square, sorry, xy minus z square plus 1, then one can show that if you adjoin one variable to b, bn, then that is isomorphic to bm for all n and m greater than equal to 1. So if you're, and bn is not isomorphic to bm if n is not equal to m. So in some sense, we have a family of examples which are stably isomorphic.
Neena, I don't see an n in the definition of Bn. What
Okay,
is?
yeah, this is x to the
Yeah.
power ny. Sorry.
Okay.
Sorry, I made a mistake. So x to the power ny. So these are stably isomorphic, but they are not isomorphic as rings. And we have a family of examples. So this was a, I would say, very good achievements. And after this, using this example, you can construct examples in higher dimension over the any field K. And so in the general, this cancellation problem, A and isomorphic to B will imply A is not isomorphic to B, does not have an affirmative solution for n dimension of the ring is greater than equal to 2. But these examples, this example of Hochster and Danielsky, if we look at it carefully, so in this example, if I adjoin one variable, they become stably polynomial. So, so a natural question which one can ask is, suppose, okay, I should better write, does there exist a ring R such that Rn is, or I should say a affine K ring, isomorphic as in K algebra to An, but R1 is not isomorphic to A1. So does there exist some ring like that? And and we know that because of Abhyankar, Eakin, and Heinzer, that this will not be true if the dimension of the ring is 1. And but dimension 2 onwards, the counter examples which you have, these Danielsky examples, they are all stably, if you adjoin one variable, it becomes isomorphic. So adjoining one variable, they become isomorphic. So the natural question is, does at all there exist some example? And the first example which we had in this direction is due to Zelonek. Let me just see. Yeah, and this was in 2009. He constructed examples over complex numbers, and the minimum dimensions were greater than equal to 10. And his example was again similar to the sort of Hochster's example, that based on the existence of projective modules which are too stably free but not stably free. And so in with Professor Asanuma, not one
it is
stably
not
free.
stably, right?
One stably free. So one stably free means after adjoining one free component, it does not become
Just
free.
add the word not.
Okay, sorry, but not one stably free. So with Professor Asanuma in 2018, this has appeared in 2018 in JCA. We had constructed an example. We have constructed an example. Okay, so Yellowneck's example was smooth. So these were in some sense good examples. So we have constructed, so dimension of the ring is 4. It is semi-normal and affine. So this was in construction. Recently, Dubolos has constructed an example. So he had completed the story, constructed smooth affine rings over complex numbers, so which probably can be extended to any field of characteristic 0. So this was over real numbers over R and dimension greater than equal to 2. So for any dimension 2 onwards, we have rings which are A2 stable isomorphic, but not one stably isomorphic. So in some sense, our example is a bit redundant, but it is good to see many examples of cancellation problems. So with this spirit, let me present you that example. So this is the example and this is the theorem. So in fact, what we have done is that we have given a recipe. So this theorem you can think of as a recipe for constructing counter examples to two stably isomorphic, but not one stably isomorphic. So K is a field and R is a polynomial ring in two variables. So I will give examples where K equal to reals and complex numbers, and this you can apply to any field provided you get all these things. Okay, so R is a polynomial ring in two variables, and F is an element in R, and S is this quotient ring, and eta is this natural K algebra surjection, and with eta n, this induced ring homomorphism. So this MNR is the set of n cross n matrices over the ring R, and this is the natural surjection induced by this ring N. Suppose, so this with this information, suppose this F and eta satisfies this property, that the units, okay, so I should say what is S star. S star is the units of S. So the units of the ring S star is same as the units of the ring R star, units of the ring R, and which is same as the, because R is a polynomial ring, so its units are same as the units of the field K. So the units must be same, and in S you should be able to find an invertible matrix P whose image in SK1. So I should better define what is SK1. So just let me go back to what this. So we all are familiar with SLNR for any ring R and an integer n greater than equal to 1. This is the set of n cross n matrices, n cross n invertible matrices. N cross n invertible matrices over the ring R. So you have a natural map from SL and R. As an inclusion, you can think that it is contained inside SL n plus 1R. What will you do? We will take a matrix M and we will send it to M 0, 0, and the last one you just add 1. So this is a natural way where we can think SL and R as contained in SL n plus 1R. So this is a highly non-commutative rings, and then we define SL of R, which is union of this SL and R. So this is the direct limit of this n cross n invertible matrices, and SK1 of R is nothing but the abelianization of this, that is you quotient it by the commutator. So this is an abelian group quotiented by the commutator of this, and so an element of this. So what we say when I say that there exists an element P in SK1 of R. So in my example, this is SK1 of S such that P is not 0. So that means P is not, so one can, so that means P is not, so P is a, so P is a matrix in SL2 of S such that its image in SK1 of S is non-zero. Okay, let me just erase everything. What is happening here? So in the theorem, we need a matrix in SL2 of S such that its image in SK1 of S is non-zero. And this is a famous result due to, probably I don't remember, I think it's Suslin, who proved that SK1 of polynomial rings, if K is a field, is trivial. So this is nothing but K star. So that means every matrix can be written as a commutator of this after some variable. So in fact, any matrix, if you take a matrix in, okay, better. So this is a theorem. So in general, so what we have R equal to K2, and from K2 we surject it onto S, and here every matrix will become stably, so trivial by non-zero I means better should say it's trivial. No, so K star is not the right thing. So K star is identity. Identity 0. So this is Suslin's result. Yeah, because or if you look 1 as the identity, then this is the 1. So, and this is S, and so we have a map from SK1 of R to SK1 of S. Even if this map is surjective, this map need not be surjective. So this need not be surjective. And our example depends on the fact that there should be a matrix P in SL2 of S whose image here is non-trivial. So then we can work with that. So let me just go back to that. So there exists a P in SL2S whose image in SK1 of S is non-zero. And further, if a phi is so R is polynomial ring in two variables, and U, V, Z are indeterminate. So if phi is an automorphism of this ring, which is an, I should say it's a K algebra homomorphism, and it fixes the element F. So fixes the element F means in some sense, the element F, so F is that special element which we have selected. So this special element is fixed. The ideal generated by that is fixed. If this is the case, then phi should also fix the ring R. So this F should be so special. So if we can choose such an F in the polynomial ring KXY, which satisfies these three properties, then we have these examples, and this is a construction of the example. So choose the matrix M in M2 of R such that its image is my P. So P is that chosen element. And then I construct this ring A. A is a R. So R is a polynomial ring KXY. And then U square V square plus F times RUV. So which is a subring of the ring D. So D is KXY UV. And inside this subring, I am considered inside this ring, I am considered these two subrings, A RU square V square and B R under this map. So alpha U plus beta V whole square and gamma U plus delta V whole square. So these are the two subrings. And if these two rings are such that this A and B are affine semi-normal domains, and A1 is then we can show that these are affine semi-normal domains. A is not one stably isomorphic to B, but A2 is a if I adjoin two variables, then it is stably isomorphic. So this is the example, and I just give a very quick proof of number 3. The proof of 2 is a bit long, so I will tell it depending on the time. So this A2 is isomorphic to B2. So for that, we use the fact that this matrix P if P is an invertible matrix, so P is where? P is in SL2 of S. So there exists a matrix P inverse in SL2 of S. So, and then construct this matrix P1. So this P1 is a matrix in SL4 of R. S, sorry. And then by Whitehead lemma, this is a very famous lemma which says that this matrix P1 is elementary. So elementary is something, let me not define. So if this matrix is P1 is elementary, then this map eta 4 has a lift. So you can find a matrix L. So this L is in SL4, which is an invertible matrix whose image is P1. So because it's elementary, we can have a lift here. So we can talk about an R algebra automorphisms of the polynomial ring RU V Z and W defined by sending U V Z and W to this linear transformation L. So L is that matrix. So this will be an automorphism. Okay, so now what we see is that this matrix, because L is a lift of this matrix, L is lift of P1, right? And what is P1? P1 is P0, 0 P inverse. So this matrix P, so for P we have a pre-image. What is that? That is my M. So similarly for P inverse, we have a pre-image M dash, but then that will be not same as this L. So it will be factored by some multiple of F. So considering that also, this matrix link automorphism L can be written as sum of these two factors, where G1, G2, G3 and G4 are polynomials in these four variables. So modulo F, it is P inverse. Okay. Now, if I apply lambda to this ring AZW, then I will say that the image is BZW, and that is very simple. You just keep applying it. So what is the value of A? A is this ring, and I apply lambda. So lambda will be applied to this ring plus this one. So I put Z and W inside this. Now applying lambda means I will apply lambda to this U, V, Z and W. So we do as it is. But what is lambda of U? So lambda of U is by this matrix formula. It is alpha U plus beta V and gamma U plus delta V plus F. And then by the same argument, because this alpha prime Z and beta prime W and gamma prime Z and delta prime W, these are linear, and this is an inverse. So this matrix has an inverse of P. We can get Z and W because we can, if at all there is a factor, we can adjoin it with F. So this will give us Z and W, and then this Z and W we can take out, and then we just get BZW. So this is very simple. And now I'll just give you a quick example over the real numbers. So over the real numbers, I can choose this F to be x square plus y square minus 1. And then it's an not so difficult exercise. And this is a theorem due to Miller. So Miller had proved that this matrix P is not trivial in SK1 of S. So using this, we see that the three properties and the other two properties one can check. So these other two properties, this one, this automorphisms fixing F will fix R, and this S star is K star. So we can check all these things for this small f, the circle, and then this is an example. So we can construct an example over the real numbers. We can also construct an example over complex number using this F. So F is y square minus x2 minus xy. So so this F is going modulo F, the ring S is this, which is a seminormal ring. So I just calculated that it's a coordinate ring. So this is sitting inside CT. And so SK1 of S is K2 of C. So this is due to, just I don't remember exactly. So he proved that this field is uncountable, where so there should be some matrix. So this matrix is not known to me, but at least there is some matrix P in SK1 of S, sorry, I should say SL2 of SL2 of S. whose image in SK1 of S is non-trivial, not zero, non-zero. So, and then we can construct these examples. So, how much time do I have? Do you have the time to prove this?
Time is actually, I think time is over. So maybe. Let us see if anyone has any question or any question from the audience. So how much time do you need?
For the proof, I need actually 10 minutes. Means the one stably isomorphic, that is a long proof.
Then maybe drop it now.
Okay.
Can
Thank
I
you.
ask a question?
Yes.
Any? Oh, sure.
This K in this case, do we assume K to be of characteristic 0?
No. So in the proof, we are not assuming characteristic 0. So all it depends on the existence of these elements.
So the ring S is a R was KXY. So the ring S is a one-dimensional algebra. It's a
No, the ring is not one-dimensional.
S.
Ring becomes 4-dimensional. So R is KXY, and the ring with
S is what? Just I was checking. S is R mod F.
S is R mod F. But
So,
the example is over R.
but what I'm saying is over FP bar, for one-dimensional domains, affine domains, I think SK1 is trivial.
For one-dimensional affine domain, SK1 is trivial, yes.
So what happens in that case? Because you said there is a P in SL2S whose image is in SK1S.
No, for one-dimensional, I am not giving you the example.
Okay.
No, but who said SK1 of S is trivial in one-dimensional domain?
Over FP bar, I think Mrinal sir's result or something.
No.
If Ravi sir is here, I think he can confirm.
No, but what about this circle? This is a result due to Milner. Means I have not proved it. So
Okay.
this is a circle, right?
But
RXY mod
He
F.
is saying over FP bar,
over FP bar.
over the algebraic closure of the finite field.
Okay, for finite field it may be.
So then
It
your
may be.
field characteristic probably matters. That's probably what
Yes,
he's trying to.
So yeah, so as I said, the recipe works for any field. I am not using, but whether you can construct an element F or
that is the question.
that will depend.
Thank you.
Sorry.
Quick request, Neena. Logistic. Could you record? Could you save these slides and then maybe email it to me after the talk?
Yeah, I will show it. Thank you.
Yeah.